Good morning everyone. Investigation of anti-lock braking system failures using wavelet analysis. To begin with, I would like to present briefly the plan of my presentation. Introduction, the ABS operation principle. Test bench setup for simulating ABS. Test results, wavelet analysis. Summary. The ABS system shown in figure, which prevents loss of wheel traction, consists of two systems, hydraulic, valves regulating brake fluid pressure, and electronic, wheel speed sensors. The voltage generated during the measurement of the rotational speed of the wheel, which is generated by induction sensors. Items 1-4 Fig, located at the rim-toothed rim attached to the wheel axis, is amplified and then transmitted to the control system. Item 5, in Fig, where the speed of all wheels of the car is calculated. When one wheel loses traction or slips, the electrical signal supplied to the steering system is inconsistent with the signals from the other wheels. The control system then sends a signal to the current regulators that control the pressure valves in the respective brake circuit. As a result, the braking force increases until one of the vehicle's wheels is locked against the others. The corresponding brake pressure control valve then reduces the braking force of the locked wheel, with the result that this wheel begins to accelerate until its speed is equalized with the others. The rotating gear rims are designed to simulate the movement of a vehicle. They are driven by two electric motors whose rotational speed is controlled by potentiometers and PWM systems. The bench includes two DC motors to which hubs have been attached, made in such a way that a workable toothed rim can be easily replaced with a deliberately damaged one. The first unit, simulating the movement of the vehicle, comprises three inductive sensors and is responsible for simulating the movement of three wheels at an identical rate. The second driving system, including the toothed rim, comprises only one inductive sensor with adjustment of the offset from the rim, whose task is to simulate the movement of the fourth wheel. This makes it possible to simulate conditions in which one wheel loses contact with the ground and starts to move at a speed different from the others, which is the trigger for the ABS to activate. In addition, tests can be carried out to determine whether the ABS system is triggered in the event of damage to the toothed rim or if the distance between the sensor and the toothed rim has shifted. The toothed rims, gear rings, intended for the tests, which are designed to move at the same speed as the vehicle wheels and are one of the key components of the ABS system, were deliberately damaged for the tests. The toothed rims were damaged based on the most common defects during the operation of motor vehicles. Here is an example of an undamaged toothed rim and damaged rims. Here are results test of inductive sensor signal in relation to vehicle speed. The tests were attempted for vehicle speeds of 10, 30, 50, 70, 90, 120 km/h respectively. For that purpose, it was calculated what the signal frequency obtained on the oscilloscope should be. After a series of testing simulations, this type of wavelet was chosen as the appropriate one for analyzing the measured signals. In order to analyze the most wanted features in time-frequency domain. Therefore, the oscilloscope diagrams represent the values as close to the vehicle speed as possible. The signals from the inductive sensor are shown here depending on the speed of the vehicle. In the figure A, speed 12 km/h. In the figure B, speed 31 km/h. In the figure C, speed 50 km/h. In the figure D, speed 70 km/h. In the figure E, speed 90 km/h. In the figure F, speed 120 km/h. So we see that the dependence of the inductive sensor signal amplitude on the vehicle speed is linear. Increasing the speed of the vehicle results in increasing of the amplitude of the signal. making it easier for the ABS controller to respond correctly if one of the wheels loses contact with the surface. The results of examining the amplitude of the signal from the sensor depending on the damage to the toothed rim. Measurements performed at a constant speed of vertical 50 km/h, and at a constant distance between the sensor and the toothed rim, that is 3 mm from the top plane of the tooth to the sensor plane. Standard toothed rim, undamaged is shown on picture A. The toothed rim with one tooth broken out is shown on picture B. The toothed rim with the axis of rotation offset by 0.5 mm from its geometric center is shown on picture C. The toothed rim with the axis of rotation offset by 1 mm from its geometric center is shown on picture D. Classical signal analysis using the Fourier transform, FFT, allows for excellent localization in the frequency domain. In some cases, it provides sufficient information about the nature of the signal. When the localization of signal features over time is required, the short-term Fourier transform, STFT, can be used. It is still based on the correlation of the signal and the harmonic function, sine and cosine, but at short intervals in so-called windows. A different approach introduces a different, as compared to pure harmonics, type of function, namely wavelets. The wavelet function and its Fourier transform with a power of 2, allow to indicate time intervals, t1 hour, phi, and frequencies, Greek letter omega 1 hour, high, containing the main amount of energy main. This is represented by the following formulae. In these cases, the centers of the areas of the integrals can be found, which indicate the central values of time and frequency. With this approach, when using the classical Fourier transform, it is not possible to locate the energy concentration in the time domain because the basis functions vary periodically in infinite time. On the other hand, the basis functions give an infinitely sharp localization in the frequency domain in the form of the Dirac delta function. A better solution is to use STFT, where FFT analysis is performed for successive parts of the signal under consideration, in separate time windows. In the case of the wavelet transform, the wavelet function shifts by b in time and scales with r in the frequency domain. Finally, the wavelet transform of any signal S, T, is calculated as follows. The dependence of the inductive sensor signal amplitude on the vehicle speed is linear. Increasing the speed of the vehicle results in increasing of the amplitude of the signal, making it easier for the ABS controller to respond correctly if one of the wheels loses contact with the surface. At low rotation speeds of the vehicle wheels, the signal from the inductive sensor has a very small amplitude, which poses a major problem for the ABS controller in interpreting the current wheel speed due to a signal that is close to the noise level. The dependence of the signal amplitude on the sensor distance relative to the toothed rim tooth plane is exponential. Increasing the measuring distance of the sensor causes a decrease in amplitude, which hinders the correct operation of the ABS, and reduces the measuring accuracy. The standard distance between the sensor and toothed rim of 3 mm used by most car manufacturers seems to be adequate. Large enough not to damage the sensor in case of a toothed rim defect and small enough for the signal to have an amplitude readable for the controller. Damage to the toothed rim is noticeable in the signal readout, which can cause the ABS system to malfunction. The results of the analyses using the wavelet analysis described above are shown in figure. The study used a Morlet wavelet, with parameter 3, which is directly related to the frequency of the mother wavelet. The greater the offset of the axis of rotation of the toothed rim from its geometric center, the greater the amplitude of the signal and the greater the noise introduced into the controller, as can be seen in figure B, where components with higher frequencies appear at specific moments in time. This is not seen in figure A, representing the undamaged system. In figure A, Only one main frequency related to the rotation speed of the toothed rim is visible. The failure in the form of a damaged tooth can be seen in Figure C, in the form of a distorted signal in one of the periods. This is precisely indicated by the wavelet analysis seen in Figure C. This shows the appearance of single signal components in the highest frequency range. A similar situation can be seen in Figure D, which shows a system with two damaged teeth on the toothed rim. In this case, two signal components appear at similar frequency levels. Thank you for your attention.